Hi! In this video, let's take a look at this battery-powered portable spot welder. I requested this from Banggood for a review. If you are interested in getting one after watching this video, please remember to check out the link included in the video description below. Now, I wanted to give you a little background on how product reviews on this channel is typically done. There are a lot of companies and sellers contacting me on a regular basis, wanting me to review their products. I usually ignore most of them, as some I think the products are questionable, and for others, I simply don't believe they are of good values. And the items I did end up reviewing were usually the ones I thought folks following my channel would be interested in. The stuff I reviewed from Banggood is also a little bit different. Most of the time I would actually request a specific item from them for reviewing, especially after doing some extensive research and found that the product is of decent quality and my viewers would be interested in. Like the Holdpeak HP 770D multimeter I reviewed a while back. So I would encourage you to leave me a comment if there's anything that you wanted to see on this channel from places like Banggood. And if there's enough interest, I will do my best to make it happen for future episodes. Anyway, the item we're looking at here today is a DH20 mini spot welder from BIFRC. I actually do not know how to properly pronounce the brand name. Not entirely sure what it means either. That's actually a problem with a lot of the Chinese products I have seen, as they do not have an easy to pronounce name that you can actually remember. Anyway, for the remainder of the video, I will simply refer to this as DH20. The package I received includes two sets of these welding tips. One set, which I have already plugged in, are these welding pens. And the other set is this spring-loaded assembly for single-handed use. This piece is marked as YXKY, and I think it's a generic welding tip assembly that can be used with different types of spot welders. Now, if you look closely, you will see that there is a momentary switch on the top, and the switch is depressed when you put enough pressure on the welding tips. So this switch can be used to control your spot welder. Of course, the assembly supplied does not have the control wire for the momentary switch. And that is because this welder senses when the contact has been made and automatically initiates the welding pulses after a short delay. We will take a closer look shortly. For those who have been following my channel for a while, you probably have seen a spot welder that I built with an old microwave oven transformer, which uses a 555 timer circuit that controls the welding pulse width. I have since used that welder many times and built quite a few battery banks with it. Well, although that spot welder is quite capable, it is nowhere near the convenience factor this mini spot welder provides. So now let's take a look at how well the DH20 does its job, and later on we will do some analysis and also do a quick teardown for a closer look inside. The user interface of this DH20 spot welder is as simple as it gets. It only has this single button to control the whole unit. By long pressing the button, you can turn on and off the unit, and by short pressing it, you can switch through the different pulse widths that you can use to fine-tune the welding time for a given material. So as you can see here, if I short press it, it cycles through. Now there are altogether 9 different settings, and it doesn't look very obvious at first, but if you take a look at the supplied manual, you will see that this corresponds to the 9 different pulse durations, which controls the welding strength. On the side wheel, you can also see that there is a battery gauge that shows you the current charge state of the battery. Of course, now it's fully charged. And by the way, you can also use this unit as a battery bank via this USB port, which in my opinion is a quite clever design. After all, you already have a battery built in. Why not add a little bit more circuitry to support battery charging as well? One feature quite clever for the DH20 is it does not require an additional trigger switch to initiate the welding. All you need to do is press both of these tips firmly on the nickel strip, and after a brief pause, the welding sequence is automatically initiated. And let's do a few welds to see this in action. So here I have a couple of nickel strips And let's see, we just powered it on. This is on the lowest setting here. So let's take a look. And I'm going to press it down. And you can see that the weld is initiated. Now, of course, let's see how strong the weld is. This is, remember, the shortest pulse duration. And the shortest duration, surprisingly, is already good enough. So it's already firmly welded together. That's actually very impressive. Let's do another one with this pulse duration. That is very, very good. Okay, so let's try with a different pulse duration. So let me increase it to, let's say, 3. And let's try again. This time I'm going to fold it over. And you can definitely feel that the pulse is longer. I'm not sure if you can hear from the sound. And it's getting a little bit violent here. As you can see that this is probably too long for a strip of this size. As you can see that we already burned it through here. Not sure if you can see that. So this is probably 1 to 2, I would say, is the recommended welding duration for your typical nickel strip of this size. And of course you can go even higher, which I would think it will be even more powerful. So let's give it a try. So this is a 5. Yep, so definitely the welding time is a lot longer, and you can see we definitely burned through a hole here. So that's obviously not the setting you will want to use for your typical welding. I think for a typical welding, the selection of 1 or 2 is good enough. Okay, I do want to test these single-hand use tips, so I just swap them in, and let's give it a try. So let's press it, and do it again. Oh, you can't see, can you? Okay, so let's try it here. And let me zoom it in. So clearly that the shortest pulse duration is definitely enough for nickel strips of this thickness, and this is definitely secure enough. Now let's take a look at how a spot welder works. A spot welder in its simplest form consists of a very low internal resistance power source. This can range from a low internal resistance battery, as illustrated here, to a supercapacitor. And then we have a switching device. Typically that's done with a high current MOSFET, as we show here, or you can use several MOSFETs parallel together. And the switching device is then switched on momentarily by an impulse generator. And that impulse can be generated from a timer circuit, which can be as simple as a discrete RC circuit, to something more complex, implemented using a microcontroller, as we show here. And that's really all there is to it. Now, the microwave oven transformer spot welder I built is pretty much based on the same operating principle, except the switching happens on the primary side of the transformer, so that the current is far less than switching along the main current path. Also, the current wave is AC in that implementation. Now let's think about how auto sensing can be achieved here. To sense that the probes are in contact with the nickel strip, all you need to do is to measure the voltage drop between these probes, as the moment you touch the nickel strip, these probes are shorted out, so the voltage drop would be 0. There's only a slight problem here. As you can see that we're using this MOSFET to switch the input to the output, and when the MOSFET is off, there is actually no output voltage. So to bootstrap this situation, we needed a resistor across the source and drain so that this resistor is large enough, there is no significant current if we do close up these leads here. And also, because there's a resistor, there is a measurable output voltage. The actual value of the resistor probably doesn't matter that much, and probably tens of kilo ohms would be sufficient for us to be able to measure the output voltage. So all we now need to do is to measure the output voltage via one of the ADC pins from the microcontroller. Now you probably see how this circuit works. When we connect these two leads, the output is shorted. Therefore, the MCU measures a voltage drop that is below a certain threshold that is predetermined, meaning that the output is being shorted. So then the MCU can generate the required pulse to turn on the switching device, in this case this MOSFET, and therefore completes your weld. Let's verify our theory here, and I'm pretty sure that's exactly how it is implemented in this device. Right now the leads are open and I turned on the device, as you can see here. And let's measure the output voltage. And as you can see, we're reading 3.4 volts. That's exactly the open voltage of a lithium-ion battery. So now let's put a 10K resistor across the output. This will be a little bit difficult as I don't have a alligator clip at the moment, but I think I would just do it by hand. So this is a 10K. Right now we're open, and I now connect it to that 10K resistor, and you can see that the output voltage dropped to 1.27 volts, roughly a third of what we had before. So just by that, we can kind of roughly calculate that the resistor across that MOSFET is roughly just under 20 kilo ohms. Next, I want you to see what the generated pulse waveform looks like. And to do that, I'm going to connect the welding tips across a 0.1 ohm resistor while observe the voltage waveform on the oscilloscope using single shot. So let's take a look. The scope currently is set at a horizontal of 100 milliseconds per division and a vertical of 20 volts per division. Now the reason is 20 volts is because we're not using times 10 probe, we're using a times 1 probe. So it's actually 2 volts per division. So let's take a look. Now I might need to do it multiple times as triggering by hand here is a little bit of touchy. So let's see here. I'm going to make connection here. Yep, didn't trigger, so let's do it again. This time we triggered, and you can see that we have this pulse on this far end. Let me expand that a little bit and put that in. So you can see that it is actually consists of 2 pulses. By the look of it, the first pulse width is about 11 milliseconds, and the second pulse is roughly 33 milliseconds. And these 2 pulses are spaced apart by roughly 3 milliseconds. Now let's increase the pulse duration and take another measurement. For that I'm going to do, let's do the 4th one, so we can see a little bit more difference here. Do it again. Try again. So this is the 4th one. Let's zoom it out and see what the second pulse width is. So it looks like the pulse width for the initial pulse remains at 11 milliseconds. And the second pulse is much longer now. Now is at 81 milliseconds. Now I just changed the pulse width to the maximum, and let's take another look. And let's zoom it out. So I fully expect The first pulse and the spacing are the same as we had before. So let's just take a look at what the second pulse width is. That's good. So the second pulse is roughly 160, 65, 66 milliseconds. So we can see that this DH20 has an initial pulse. The pilot pulse is roughly at 10, 11 milliseconds, and then there's a 3 milliseconds delay. After that, the pulse range is between 30 to 160, roughly in 10 milliseconds increment. So that's the 10 different durations you can achieve with this spot welder. Another fun thing I want to do is to measure the actual output current from this spot welder. And for that, I'm going to use the impulse current measurement from my Kaiwi's clamp meter. When I reviewed this meter a while ago, I did not actually measure the inrush current capability of the meter because I did not have a way to reliably generate an impulse current. Now, with this spot welder, I think I can definitely do that. In order to make sure that the clamp meter is actually measuring the correct current reading, I'm going to first use this 1 ohm resistor to calibrate the reading here. And because this is a 3.4 volts output battery, we should read the peak current at 3.4 amps. So it doesn't really matter the pulse duration. That's what I'm expecting from this Kaiwi's current meter measurement. So let's turn to 600 amps. I think that's plenty. And that's, let's see. So this is for inrush. I'm going to clamp it on, and we can see that. So, with any luck, let's try to. Yep, as you can see, that we're reading 3.69 amp. So that definitely means this Kaiwi's meter is able to pick up that inrush current flowing through this welder. So very good. So with that out of the way, let's do some real measurements. And these are some of the nickel strips I used in our tests earlier. And let's see what the current is when we do the real welding here. So let me clamp it on. This is the inrush reading. That's so you can see that right now that current was 388 amps. So let's try it again. Let's fold this over. And this one is even higher, 427, because I pressed it in harder, and also probably the resistance is, the distance is shorter. So let's try it again. This is a lot of fun, actually. And also you notice the other nickel strips jumped, because when the high current flows through this conductor wire, it generates a magnetic field. That's why these strips are jumping here. So let's do this one. 349. $408. Now let's open it up. The circuit board is fairly easy to access. Once you remove either side of the panel, the circuit board just slides out. And you can see that the aluminum case used for this unit is really nicely machined here. Now let's take a closer look at the board. The most prominent feature you can see here are these 4 MOSFETs. I can't find the exact model number, but these are N-channel MOSFETs, so the arrangement is a little bit different than what I illustrated before. Instead of switching on the positive side, the high side, this is actually switching on the low side. You can see that ground is right here. this arrangement does not require a dedicated gate driver, as if you put an N-channel MOSFET on the high side, you will need to drive above the rail for the MOSFET to turn on. There are, of course, dedicated gate drivers for doing just that, but a simpler approach is as what is implemented here, which just switch the low side instead. You can also see that there's a microcontroller chip here that is marked as a STC15W404, which is an 8051 based microcontroller that also has 10-bit integrated ADC. And clearly the ADC is used for monitoring the output voltage and detect whether the welding tips are in contact of the nickel strip. There's also an unpopulated UART header here, which probably can be used to monitor the various statuses, as I don't believe the STC chip actually uses the UART to do the initial programming, but I could be wrong. And here we have an IP5306, which is an integrated charging and discharging controller, which is obviously responsible for charging the battery and also provide the 5-volt USB output as a battery bank. This chip also drives the battery charge state LEDs as well, as you can see in the reference circuit diagram here. And we also have a photocoupler, PC537 here, by the look of it. And here we also have a buzzer. Because of the high current, notice that the bus bars for the drain and the source of these MOSFETs are further beefed up via these copper bus bars. Now let me turn this over. You can see the backside. Of course, there's not much to it. You will see that on the backside, the battery is actually soldered onto the PCB, and there's no protection circuitry on the battery terminal itself, and everything is controlled by the charge controller. This arrangement can be quite dangerous if you disassemble the unit as I did, and if you somehow accidentally short out the battery terminals, it will be a disaster. But when enclosed in the enclosure, it should be fine, as it is safe enough to be flown on an airplane during shipping. In my opinion, using the battery directly to supply the current required for welding has some drawbacks. As the battery ages, the internal resistance would likely increase as well, and the battery may not be able to provide the high current required by the weld as it ages. So it would be better, in my opinion, to include a supercap, but of course it increases the overall cost a little bit. So that pretty much concludes this review. I hope you enjoyed the video and learned something new. If you liked the video, please don't forget to hit that like button and remember to subscribe to the channel for more content like this in the future. I will catch up with you next time.